We will investigate the applications of ultrasound waves. Specifically, we will focus on the medical applications of the ultrasound waves. One of the mechanical waves is sound wave. The mechanical wave is transmitted through a medium by molecules. The mechanical energy of a wave causes molecules in a medium to vibrate, and this vibration is transmitted to surrounding molecules in a sequence of processes. As a result, the mechanical wave cannot propagate without the presence of a medium. On the other hand, electromagnetic waves do not require a medium for propagation. A sound wave's frequency is determined by how fast its energy source vibrates the medium. The frequency of sound wave is measured in Hertz, which is the number of vibrations per second. The human ear can only hear sound waves in a narrow frequency range, namely 20 Hz to 20,000 Hz. Sound waves with a frequency greater than 20,000 Hz are commonly referred to be ultrasonic waves. The density of the medium through which the sound wave passes determines the speed of sound. The denser the medium, the faster the sound travels. This makes sense because the denser medium has more molecules involved in the delivery of sound waves. Let's look at how sound waves move through the air. The mechanical energy source of sound wave causes nearby air molecules to vibrate. The vibrations of these molecules are conveyed successively to their neighboring molecules, result in formation of denser and less denser region of air. The formation of sound wave is seen when powders in a tube are vibrated by a speaker as shown in the figure. So sound wave is generated by the speaker and then the powder is moving this direction, so vibration, and we have a dense region and less dense region. So the speed of molecules or the air molecules at this point is 0, and in between these 2 points, the speed of molecules is largest, and at dense region, molecules are stationary here, so speed of molecules is 0. So these patterns of speed are continuously formed through the media, and the pressure is highest at this position because we have more molecules here, so largest pressure and 0, and at this position there's no molecules, so it shows the lowest pressure compared with the average pressure. It shows lowest value and highest value and these patterns continue through the medium. Okay. The direction of molecular vibration is parallel to the propagation direction of sound waves, as can be shown. So vibration of the molecules in this direction, longitudinal direction, and the sound wave propagate in this direction. So direction of vibration and direction of propagation are the same. So in this case, we can call this wave as longitudinal waves. Therefore, the sound wave is called longitudinal wave. Now let's see how ultrasound waves are generated. We must vibrate the medium's molecules over 20,000 times per second to generate an ultrasonic wave. Electric or magnetic restriction materials are used to create the ultrasonic wave. The size of these materials is affected by an external electric or magnetic field. Typically, an ultrasonic wave is generated by applying a time-varying field to the electrodes on two sides of a thin plate of restriction material. A permanent electric dipole exists in electric restriction materials, also known as piezoelectric materials. These permanent electric dipoles are oriented at random in the absence of electric field, but they are ordered within one. When dipoles are placed in an electric field with the right-hand direction as illustrated in the top view, this view, we applied electric field along this direction. Then the material expands following the field direction, that is to the right, because electric dipoles are arranged aligned to the field. So over length of the material extend. So the extension direction in this case is to the right direction, to the right. Okay. If the field direction is reversed, so in this direction, now to the left, as illustrated in the bottom figure, this figure. If a piezoelectric material is subjected to an alternating voltage source, the material size oscillates between its maximum to the right and the minimum to the right lengths, which corresponds to positively and negatively maximum values of the applied field, respectively. So if we apply alternating electric field to the piezoelectric material, then this material oscillates to the left and to the right. So material's size is changing to the left and to the right, to the right, and to the left. So it oscillates. So change in the size of transducer material due to the alternating voltage. The frequency of the applied field is the same as the repetition of this oscillation. The frequency of the applied field, however, must be close to the natural frequency of the transducer material for proper oscillation, otherwise the material will not respond. The material type and the transducer structure both affect the natural frequency of the transducer material. For example, we have this relationship Ft equal 2780 can be used to calculate the natural frequency of the quartz rate with a sequence of the T here, T and F are measured in millimeters and 1000 Hertz respectively. The value 2870 represents the thickness frequency constant, which is the characteristic quantity of a quartz. The ultrasonic wave is generated by the alternating change in the size of the transient material, which causes molecules in the medium to vibrate. The mechanism for producing ultrasonic waves with magnetic restriction materials is the same for that for piezoelectric materials described above. The only difference is that magnetic restriction materials have permanent magnetic dipoles, allowing the size to be altered by applying a magnetic field. So in the piezoelectric material, there are electric dipoles. So electric dipoles are aligned to the direction of the fields. So the alternating electric field is changing its direction, so the size of piezoelectric material oscillate. The same principle can be applied to the magnetic restriction materials. Magnetic restriction material will have permanent magnetic dipoles. If we apply the alternating magnetic field, then the permanent dipoles are aligned to the field. So field is oscillating, so the size of the material is also oscillating. If the size of material is oscillating, then the molecules in the medium are oscillating, and the ultrasonic waves are formed. Quartz is a common material for transducers. Many ceramic materials for ultrasonic transducers have recently been developed. These ceramic materials include PVADF and PGT. PGT consists of red zirconate, titanate, and the compounds of P, Cl, and TiO3. Many industrial and medical transducers are being replaced by ceramic transducers since ceramic materials are convenient for making transducers for any shape. The PGT material in particular has a very high extrusion ratio, roughly 160 times that of the quartz, and is thus widely used. So PGT materials are now widely used for medical application or industrial application. Magnetic extrusion transducers are commonly made of nickel ore and ferrites. The molecular formula for ferrites is MoFe2O3. Here M stands for iron, nickel, cobalt, and Va. Ultrasonic waves in the kilohertz frequency range are produced by magnetic extrusion materials, whereas ultrasound waves in megahertz frequency range are produced by piezoelectric materials. So the frequency range are different. For the magnetic electronic material, the range of the ultrasonic wave is kilohertz. On the other hand, if we use piezoelectric materials, we can produce ultrasound waves in the frequency range of 1 megahertz. The table below lists the most commonly used ultrasound transducer materials. The frequency range refers to frequency limits imposed by shape of transducer, especially its thickness, as well as the amplitude of the applied field for oscillation. There are two kinds of transducer material: electric material and magnetic materials. In the electric material, we have quartz and the ceramic material, PVDF and PZT. Its frequency range is given here. So megahertz for electric material. And the electrician ratio, or delta L over L, is for quartz, for example, 2.3 times 10 to the minus 12. This restriction per volt. Magnetic material, we use nickel and ferrite, and its frequency range is kilohertz. In the electric material, we can have megahertz, but for magnetic material, we can only have the ultrasonic sounds of kilohertz range. The figure depicts the schematic diagrams for the generation and the detection of an ultrasonic wave. The transducer's electrodes are connected to high frequency voltage source. So that is the ultrasonic transducer material, usually a thin plate, and then you can make electrodes on both sides, and we apply the high frequency voltage source to the electrodes. Then the plate then oscillates, which causes the molecules in the medium to oscillate, resulting in the generation of ultrasonic wave. So this plate is oscillating. Then this oscillation energy is transferred to the molecules in the medium. If we use this ultrasonic transducer in the air, then propagation medium is air molecules. If you use this transducer in the water, underwater, then propagation material molecules are water molecules. The technique for detecting ultrasonic waves is the inverse of the procedure for producing ultrasonic waves. When ultrasound waves passes through the plate, it causes the plate to oscillate in response to the wave source. So wave source is coming, then this ultrasonic wave vibrate the plate of transducer material, and the dipoles inside material, the dipoles inside material plate oscillates and causing the voltage across the plate, which is measured. So in this way, we can generate ultrasonic wave, and we can detect the ultrasonic wave. So generation and detection of ultrasound wave. The figure shows a schematic diagram of ultrasound transducer. It shows the ultrasonic transducer. A pulse generator is connected to the electrodes to supply the voltage to the transducer material, which is sandwiched between two electrodes. So transducer material is sandwiched between two electrodes, and the pulse signal is given to the two electrodes here and here. We can supply voltage. To increase directionality of the ultrasonic wave, the lens is placed in the direction of sound propagation. So this one. So a lens is made to improve the directionality of the ultrasonic wave. The sound observing substances, on the other hand, is placed on the opposite side of the lens to observe sound waves in this direction. So sound wave is propagating in this direction. So in the opposite direction, we have to observe the sound wave by some sound observing material. Now let's see how the ultrasonic imaging is performed. The basic idea of ultrasound imaging is similar to that employed by bats and dolphins to detect obstacles in their path. Ultrasound is emitted by bats and dolphins. The ultrasonic wave is then refracted back from the object in front of them. They detect the refracted wave and use the time between the emission and detection of the wave to determine the object distance. So we can use the same principle for ultrasound imaging. Ultrasonic pulse, usually 1 to 5 microseconds, is sent to the body for ultrasound imaging. When this pulse encounters with tissue surfaces, tissue boundaries, or organ structures, it scatters in all directions according to the rule of the refraction. A fraction of the pulse energy is reflected back to the ultrasonic wave's original transmission direction. If the ultrasound meets the tissue boundary, then ultrasonic waves are reflected in all directions. And some of them are reflected back. This one. So it's going this direction and the same direction, opposite direction. Is there is the backscattered. So this back scattered pulse energy can be detected by the same transducer that emits the ultrasound. So we can measure this backscattered ultrasonic sound wave. After detecting the backscattered signal in one position, we move the transducer to a different location and repeat the process. In this transducer, we have several ultrasonic sound and ultrasonic detector. So transducer is composed of many ultrasonic detectors. So in this case, we can measure the backscattered ultrasonic sounds for 3 different positions. If we have just one, if we use just one ultrasonic detector, then we can measure at certain position and move this to other direction to measure the same procedure. The time delay between pulse transmission and the backscattered signal detection, as well as the speed of sound through the body, which is approximately 1540 meters per second, can be used to determine the depth of the boundary. So we can use this time t, t1, t2, or t3. Then we can, using this one and the speed of sound, we can determine the position of the tissue boundary. If we detect the backscattered signals at enough locations, we can construct an image of the boundary. So this image boundary can be formed by using the enough data of the backscattered signals. The intensity of ultrasonic waves propagating through the body is attenuated at a rate of about minus 0.5 dB per megahertz centimeter as they goes through the body. The majority of the attenuation is due to tissue absorption of the sound wave. If an ultrasonic wave of 3.5 megahertz is employed, for example, the intensity of the ultrasound wave is decreased to 1 over 7.5 of its original intensity at the depth of 10 centimeters in the human body. The sound reflected back from the boundary at the depth of 10 centimeters is received by transducer in this example above. As a result, the sound detected by transducer has an intensity of 1.7.5 times 1.7.5, just gives the 1.56 that original sound wave. This shows the absorption when ultrasound wave going through the body 10 centimeter, and this attenuation 1.7.5 is the absorption by tissue molecules for coming from the tissue to the transducer. So we have just 1 over 56 of the original sound wave can be detected for the backscattered sound wave of the 10 centimeter depth of the body. The frequency of the ultrasonic wave is inversely proportional to the rate of attenuation. As a result, the higher the frequency of the sound wave, the more difficult it is for it to penetrate the body. If 7.5 MHz sound wave is utilized, the intensity of the sound wave reflecting back from the boundary at depths of 10 cm is reduced to 1/5600 times its original intensity. So we saw that here for the ultrasonic wave of 3.5 MHz case, the detected intensity of sound wave is reduced to 1/56 that of the original sound wave. But in the case of 7.5 MHz sound wave, we can have just 1/5600 that of the original intensity. So the signal will be very small, so it's hard to make image using this data. So as a result, whereas lower frequency ultrasound typically between 3.5 and 5 MHz is used to examine the deeper section of the body from the skin, the higher frequency wave of 7.5 MHz is useful for observing the shallow regions. Okay? Because for higher frequency ultrasonic wave, the absorption is more than that of the smaller frequency ultrasonic wave. To achieve a clearer image, ultrasonic waves must be focused to a specific depth of the body. When an ultrasonic wave travels through the body, it is scattered by all of the boundaries it encounters. So the time it takes for backscatter signal to return from the same boundary surface at a certain depth is used to identify them. If an ultrasonic wave can be focused on the region we want to view, the boundary surfaces from which the sound wave is reflected can be more precisely defined, resulting in a clear image. So we have to focus ultrasonic sound on the sound region we want to view. As discussed before, for a smaller ultrasonic frequency, we use the this ultrasonic wave for check the shallow region from the skin, and for higher frequency ultrasonic wave, we can use that to check the deeper organ from the skin. The ultrasonic wave can be focused in two different ways. The ultrasonic beam is first focused using a spherical shaped transducer or an acoustic lens on front of the transducer. Second, as illustrated in the figure below here, the electronic delay to the linear array of ultrasound transducers is used for focusing. So we use the array of ultrasonic transducers and use the delay of the delay of the emitting the ultrasounds. A linear array of transducers can be used to simulate an ultrasonic lens by assigning each one a distinct operating time delay. If the transducer at the center is operated after specific delay time compared to other transducers, the sound wave generated by a linear array of transducers converges to a specific distance of focal length. So in this way. And this operating delay time is successively decreased as we go to outer transducer. So here the center has largest delay time, and if you go to the outside, the delay time become less and less. Then ultrasonic sound will be focused at a certain position, at which you want to see the tissue or organ. So focusing of ultrasound waves by applying successive delays to the linear array of transducers. The sound wave reflected back from a deep tissue boundary has lower intensity than the sound wave reflected back from the shallow tissue boundary. That's obvious. The deep tissue boundary's backscattered signal must be increased to match the shallow tissue boundary's larger backscattered signal. If the amplification gain is tuned to increase with time, the intensity of the backscattered signal from deep region can therefore be boosted to the level of the signal from the shallow region. This process is referred to as TGC, time gain control. This table shows the various scanning types. If you use this kind of sensor, so each one has a transducer. So we have the several transducers. Then we can scan in this direction, and then we can observe the wide range of the ranges by this by using this kind of sensor. And this shape of the transducer, the crystal oscillator arranged in the circular type, then we can we can detect actually the wide range at the time. This is just one transducer, so we check the region in this way. If you use this kind of transducer, so each one shows the transducer crystal oscillator, each one. So there is arranged in two-dimensional array. This is just one-dimensional, so just one-dimensional. But this transducer has the two-dimensional. So using this kind of transducer, we can get three-dimensional imaging. And this transducer is curved, but this one is rectilinear two-dimensional transducer, and the scanning will be this way. So also we can have three-dimensional imaging using this kind of transducer.